Greg, I'm not understanding. It's showtime? I can't hear you. All right. It's showtime. Let's go. Better together. All right. Take it away. I guess I take it away. I'm driving here, so let's drive. Oh, there. Okay. We got a packed agenda. I was assuming we had more time than we do. So at any rate, we'll use up the time we got. And this is based on Semantic Scholar. We really appreciate how they've been very, very good at sharing data. And it's a significant effort. They got a lot of documents. I'll refer to it as 200 million, but it's more than that. And people say it's all computer science. No, it's not. It's a lot of things. It's pretty heavy into STEM, though. It's not so good in English. Anyway, did I say we have a GitHub? And yeah, right. I'll answer questions about that later. Okay. Now, these slides are on the GitHub, so if you want to click on any link, you can do that, or you can use the QR code without it. And I want to point out we now have a web service thanks to Amazon and Hopkins. And all right, well, thanks to all the people. I'm sure Sanjeev will make sure that all the sponsors get noticed. Yeah. Here's the web page, and you can get there by the QR code. And here's an example of using the query is the deep walk, and it gets the deep walk paper. And here it had 7,000 citations. And here's some suggestions of papers that are highly cited. And then I have another feature where you can add the and embedding equals Spectre, and then you get the Spectre alternative. And notice the Spectre alternative doesn't have so many citations. So here I put the two side by side, and you can see that the prone method has more citations than the recommendations from Spectre. Spectre's matching on the text, and prone is matching on the context. And we're saying here, there I'm showing you some text, which is the author's perspective. That's the author's perspective. And then prone is looking at the links, the audience perspective. And we're arguing there's a better together story, and you should use both. And there's some interesting questions about how to combine them. And I'll let others on the team discuss that. Here's another famous query I like to use. No, this is the deep walk one I already talked about. And my point here is that papers with more citations are probably to be preferred over papers with fewer citations. Now this top one, the one that's recommended by Spectre on top, has no citations. Why did it come up with that one? It turned out that the paper that it's recommending that has no citations is written by the same guy that wrote the query paper, and the abstract is identical. All right? It's a dupe of the paper that was published, but the second one, the one that has no citations, was not published, but it's still in the database. And I want to say that a dupe matches, the abstracts match wonderfully, but it's a terrible answer. Okay? So for recommendations, I don't want to look at overlapping words. That's not enough. I can have two matches that are dupes match perfectly in terms of words, but they really don't answer the question I'm interested in. What should I read or what should I cite? I've already read the query paper. What other things should I read? Okay, and then don't give me dupes. And I want to say the things that you should return should be things that are credible, that is highly cited. Most papers are not highly cited. Most papers aren't worth reading. Don't show me a paper that's not worth reading just because it matches the query. All right. Here's Emily Bender's paper on stochastic parrots. You probably heard about it. Pretty highly cited. And the things that are proposed by the prone method on the bottom are all about toxicity. The ones up higher are sort of vaguely on deep nets, but nothing really about toxicity. And so and toxicity is kind of an important aspect of the query paper. So I want to say that, again, matching on the words in the abstract just isn't enough. We got a lot of deliverables. I'm not going to discuss all of them now. We'll come back to this slide. But if you're on the YouTube and you want to know how to find any of these, you got the QR code. Or did I say we have a GitHub? Anyway, now, spoiler alert, where are we going? And what we've got in multiple representations, we've got text and we have context. And I want to say the multiple representations are useful for dealing with missing values, and we got lots of missing values. I think Sanjeev already kind of described this point, but you should use what you got. When you got abstracts, use them. When you got links, use them. When you got both, use both. And when you got neither, that happens 31%, find something else. Okay. Now, another point I want to make is that there's this question, which is better? And I want to say the standard way of answering this question is to pick a benchmark, usually a single point, chosen very badly, and then you make the generalization that one's better than the other at that data point. And we want to say, no, the story's far more interesting than that, and stay tuned. Opportunities. Many benchmarks focus on a single point, a single figure of merit at a single point, and I want to know what goes on over a curve. How do these things scale with the size of the problem, and how do they scale with how much I'm trying to forecast? And forecasting is hard, and forecasting farther into the future is harder than forecasting a little in the future. All right? Now, missing values, as I say, lots of these systems tend to focus on the intersection. Prior work like Spectre is really designed for the area where I have abstracts. Some other things only work where I've got intersections. We need to come up with solutions that deal with the union. It'd be better if we could deal with the whole problem, but I'll be okay with dealing with the union. Opportunity. I want more realistic benchmarks. So the real world is large, growing, messy, and the benchmarks have none of that. Okay? Here's the notion about large and growing. So in fact, it's been said, and I think this confirms, that the literature doubles every 9 years. Okay? So 90% of it was written since I was in graduate school. The circles are the observations. The red line is the doubling every 9-year prediction with 2 different initial conditions. And I want to say the circles are kind of in that region. A standard benchmark like OGB, Open Graph Benchmark, is tiny, and it's frozen from a meeting that it was prepared for. And the web companies know they need to keep things up to date and that the web is a moving target. I want to say the problem we're working on, academic search, is pretty much the same problem. All right, you just can't deal with a tiny benchmark from a few years ago. It doesn't generalize. I want to say the same thing not only about Open Graph, but also some other evaluations, SciRep Eval. That one was frozen from there, and Semantic Scholar is bigger and growing, has lots of missing values. And here's this SciRep Eval is designed. It has the intersection's got 80% of the benchmark, but in Semantic Scholar and the problem, it's only a third, only 30%. So these things are just not representative of the bigger problem. Now, Rodolfo, who's coming soon, is going to talk about how do we estimate vectors for new papers that are not in the training set. And one of the ideas is, let's say f of d is a document, f of d is a vector. How do I estimate f of d when I don't know what it is? All right. So and one suggestion is you just can't do it. We've got 2 suggestions. One we'll call better together, and the other I'll call the centroid assumption. The better together is to use the links when you have them and use text when you don't. All right. And then the centroid assumption is if you don't know D, maybe you know the vectors for its references, and you can infer the document from its references. Rodolfo will do that. The centroid, here I'm showing some evidence. So I'm comparing f hat of D, which is the inferred value of f of D, with the actual f of D that I know. And in the proposed method, the cosine's pretty good, which means that the approximation is pretty good. We'll show a lot more evidence for this. Anyway, now, this is a bit of a digression. Approximate nearest neighbors is kind of important, and I don't want to spend too much time on this, but for those of you who are know about annoy is a really good thing to know about. If you don't know about it, look it up. If you do know about it, then maybe I can move quickly through this. But one of the things that annoy does is does everything in memory. These objects I'm dealing with are like almost terabytes in size, and I want to be able to create the index by streaming. I don't want to actually have to read the index, the whole thing in to create the index, and I can't keep the indexes in memory. There's a bunch of external memory things I want to do. This is a little documentation describing annoy, and it's a good thing to know about, but it basically makes it so you can create indexes, and then you can use the indexes at query time. So what the query does is I give you a vector, say Q, and I want you to find some candidates C that are near Q and return the n best that are the best cosines. And annoy comes up with a very nice answer to this, but it does it using lots of memory. What I'm going to say is that what the index is can be treated as pi. It's just a permutation of the integers from 1 to n. And I can create a separate pi in a separate process. So the only thing I need to communicate between processes to get different pi's is the random seed. And that means, and then each of these processes can run basically by streaming the embedding through. So I don't even need to keep the embedding in memory ever, all right, to create the index. I also don't need to keep it in memory to use the index. Now, I don't want to spend a lot of time on this, but if there are questions, I'm happy to explain that. One of the tricks is memory map. This is probably not well known. There is a memory map function in NumPy, so you don't actually have to use the C to use it. And what memory map does is it says, I can take that embedding, which is a giant binary file, and just add it to my swap space. I don't even have to copy it from disk. And then I can do random access in it as if it's an array. And as long as I don't touch any page, I don't pay anything for it. So I only pay for the pages you touch, all right? And this is an incredibly powerful thing that makes a lot of what I just was getting at very easy. So there's a bunch of problems I want to be able to do in external memory, like how do you create the indexes and how do I find the n best answers? And all of this can be done in external memory. And the only thing I need to do, and separate jobs, it's embarrassingly parallel. So each index can be generated in a separate job. The only thing that needs to be communicated across jobs is the seed. And as long as they all have different seeds, I get different indexes. One of the things that's often done, so I'm going to represent the n by k floats as n by b random bytes. And the bytes encode the floats, and usually you want b to be big enough that it can capture the information in the embedding. But actually, I just need b to be big enough that the pi is well defined. And as long as I get a different b for every different process that I do, because I use a different seed. So that means the b can be tiny. I use 6 bytes when in fact k is much bigger than 6, right? And that n by b is the only thing I keep in memory. And from that I can generate the pi. All right, I know I'm going very fast here. I don't really want to spend a lot of time on this, but I'm happy to talk with people who are interested on it. This is something to show what's sort of well known, which is that Hamming distance on the random bytes are a pretty good approximation of the cosines, so that if you sort by the random bytes, you actually get the right answer. Now, this is the new thing that's actually not in annoy, and that is that treat M as an embedding. It's an n by k matrix. That's a terabyte. All right? N is 200 million. If I multiply M by M transpose, I'd have a 200 million squared dense matrix. All right? That's not going to happen. All right? So I can't materialize that, but I can materialize the large values. So there's n squared values in m times m transpose, but there's only n values in each of those indexes. And if I only have to iterate over the indexes, it's a linear thing. So I can find the large values in m times m transpose in linear time, right? Most of them. And that's what we're really using. So this scales, whereas I can't multiply m times m transpose. All right, that was Whirlwind. I know I went too fast. I'm happy to go over that slower and if there's any questions. We're going to now go to Rodolfo.
Good afternoon. Ken. I'm going to talk about related word hypothesis. What is related word hypothesis? Nowadays, there are expector, expector2, prong, link BERT. Okay, but it's possible to use those models in new paper. Okay, what do you mean by new paper? This example show is the reality when we need use different models like expector2, expector1, and prong. Okay, my paper in this example is talk about Quechua language, low resource, the view language model. Okay, but what need to define similar papers using my papers? Okay, but that the new paper has an idea to create this vector in expector2 or prong model. The answer is no, it's possible now. But so how to create a vector on my new paper? Okay, our solution is using the O reference in my paper. Using a specter or prong, get the vectors of each my reference. Then apply central method to create the new vector to represent my papers. Okay, then using my new vector, we can find similar papers using the different method nearest neighbors. Okay, and the output is a recommendation. For example, using our reference citation, we can see using a prong model and a spectrum model. You can see there are the two examples. And the first is like talk about Turkish is for similar. My paper is Quechua and Turkish is a similar. Roberta is mentioned in my paper. It's good, but using expector2, no. But only talk language model are pertaining. But transformers and math language is not good using expector2 in this case, using central method, forget the new vector. But okay, this example use O reference. What happened is use not only O reference, use only related word reference. Okay, but using only related word reference, the results are closer to my paper. It's similar, but in the prompt, talk about the Turkish, monolingual, okay, and expector is so different. It's the pertaining performing max language. Okay, it's very cool. But what happens if I don't have the related word reference, but it's very complicated to get only related word reference? Well, apply clusterization. And clusterization is a good way to get only related word reference. Using only related word reference, we got more closer papers. For example, using prong is talk about the low resource languages is most close. And a specific paper in Quechua. Spectre 2 only explain BERT and Roberta. Okay, but it's only the mention of result, but it's better using related word than all reference. Well, in the second experiment, using not only one paper, using 400,000 papers. This file is organized by Martin. This corpus mapped to semantic scholar IDs. Okay, using an expected to a prompt model that get centroid using related word and non related word or reference. These graphs show examples of reference vector. BOL is the centroid vector using all reference, and BRW is only related word vectors. Okay. Okay. Now, in this experiment, first get the B model. The B model is the vector if model prong and expected of represented to my paper. And BOL and BERT is only using a centroid vector. Okay, and compare using Cosines similarity. And well, this graph that you can see using related word reference is 74% more better, and using all reference is very interesting, but it's only in prone case. Okay, and using expected to is similar, 70% times is a better use only related word reference, all reference. Okay, now the first is what happens if I don't have ID or index for create my new vector and use related word reference. Now, it's possible to predict the new vector on the B model. Is a good question, I think. Well, in this case, using create two models, using the central vector for related word reference and non-related words, and only use related words. We build a new neural. It's very simple to predict the B model. We use Martin's file, our neural network trained with specific hyperparameters, you can see. And in the result is very interesting, I think. You can see in the 76% times is better use be predict is the vector of the predict is more close to B model in this case. And well, in second experiment is use both the vector of related word and vector all reference is more better, but okay, conclusion. Central vector is the reference approximate to vector of the model. You know now, the central vector of related word reference is better than use all reference. I think is the most important conclusion. Is only use related word, is more fast, is more closer to vector of model. Using a clustering model helps to get a related word reference in case you don't have them. The vector generated by the neural model is close to B model than the vector of related word reference. So we can apply this centroid method in the web can mention. Thank you.
Good afternoon, my name is Shabnam. I continue our work with emphasizing on the aspect of a scale. When you scale, you both deal with the pain and the gain at the same time. So we create some pain, and the pain is to deal with the big scale data. And this is going to be presented by one of my teammates, Ben, shortly right after me. But from that pain, we gain a lot, and this is the network effect, which is going to be presented by other teammates right after the break. So at that point, I'm very going to focus on the pain, which is after me, and then the gain comes after the break. So the gains involve the Metcalfe's law, and in there we are talking about the economy of scales, which focus on both costs and benefits. Cost scales the nodes, and benefits scales the edges. So imagine the fact that you own a phone, or you want to buy a phone to connect to a network. When you buy a phone, you pay for only the unit of the phone. You pay for only one phone. But the benefit is you're actually connected to the whole network. You can call anybody who you like. We want to emphasize that Metcalfe's actually won the Turing Award. Along with Metcalfe's, we would like to focus on two more areas, which is deep nets and linear algebra, and these are very important to the problem that we want to solve. So the focus here is the linear algebra, because nobody knows the Dangara. So Dangara contribution to our community is to create the work that can be used to implement the algebra theory. These three are very, very important for the problem we solve. I would like to continue to introducing some opportunities. We would like to encourage the community to think about solution to the real solution to the problems. Literature happens to be more relevant than it is. And usually it focuses on very small and clean data, which is not scalable, while we have to deal with the realities, and we want to scale. Reality is literature is large and it's growing, and data has issues. Data has missing values and worse. And when we want to scale, basically talking about 1 point, which is the benchmark, which is done in benchmarks, it's only 1 point, while we are really care about the curve. I promise after the break we are going to answer all of these questions that you see in these slides. So you've seen that slide before. This is probably very important that we repeat many times. So better together conjunction, you have multiple representation, you have link representation, you have text representations, and there are missing values. So when you have missing values, of course, the suggestion is use one over the other whenever you've got them. There is a trend here that when use one over the other, which is again going to be presented by my teammates after the break. So we are very much interested to know when we can use one over the other, and the trade-offs is very, very interesting. So in this example, you see number of papers. They all, they each cite one after in the chart, of course. This is an illustration of what we actually suggest for the split of test and train. What we propose is you draw a line in time between these papers, and anything before that time should be considered as train, and anything after should be considered as test. This is our proposal. Now, what's done in the literature traditionally is a random split of test and train, and they have a point. So pretty much the ML community very much focus on the fact of interpolation. Well, we really, really are interested on the extrapolation and forecasting. So, and also again, after the break, we're going to show the forecasting, and we show that the short-term predictions are much easier than long-term predictions. So in this slide, you will actually see a very important but painful construction, the constructions of bins, which is going to be handed off to Ben. After me, he's coming here and talk about his challenges and how he actually overcomes some of those challenges to have this construction. But as you see, we have the beans constructions, and they are over time. And this is going to be presented by Ben very shortly after me. From there, we actually constructed our graphs. And now we have both of them. Again, Ben is going to talk about all the pain. And I'll promise, really, after the pain, there will be the gain. So I would like to close my presentation with saying that we create the pain and we overcome the pain, but after that, we use everything that we produce to gain really interesting results, which you can have a coffee and come back and enjoy the results that my teammates presenting. No coffee until after the Ben. Okay. Thank you for your attention. I can take some questions if there is any. If not, I hand the microphone to Ben to talk about pain.
Oh, there's a question though.
Okay.
So is there any issue with this time fuzziness of publication of papers? Because sometimes we have a paper that shows up on archive, it gets published at a conference or in a journal 2 years after that. So is this an issue for you?
It's a huge issue, but worse than that, there's a lot of papers that I have no idea when they were published. I think Abtine found that 2% of the publication dates we have are wrong. Okay, so data's dirty, all right?
I thought the problem was not that the date is wrong, it's just that people can sometimes cite papers in the future.
Oh, that happens too, right?
Right, yeah. I did have a couple of questions as well. Actually, Rodolfo, I had a question for you. One of the things I was thinking about is I think you convinced us that if I have a new paper which doesn't exist already in my graph embedding, then of course I don't know how to represent it. Mm-hmm. But what you can do is you can instead take, it's a one-way thing, but you can take the references that this paper cites, mm-hmm, and then do something with their embeddings to come up with an embedding for this paper. Yeah. And then within that you showed us something else, which is that if I use the papers in the related work section, exactly, then that's even a little bit better. Okay, good. My question was, how much of it depends on the author of that paper doing a good job of citation work? Because in some sense you're assuming that the author has done a good job, and that because what that paper is still missing is citations to it by other papers, yeah, because that are going to come even further in the future. So your FD, the reference with which you compare, does that also take into account papers in the future that cite it? Or is that a one-way? What is your reference? What's the gold standard that you're trying to achieve?
Yeah, in this case only, if my paper is possible to get the vector of the reference using, but it's not possible. Okay, but you don't want to check? Okay.
I would say stay tuned until Peter presents his presentation, because he really addresses the question we were getting at, which is how to split the test and train really nicely.
Right. Also, I'm also thinking about how to get the gold standard. So if you said, once my paper has been published, if I throw it back in the graph and relearn my graph embeddings, I will know how to represent this paper.
And that's what Peter's going to do.
Right. But the thing is that that embedding might have papers in the future as well.
There's some, because okay, there's some problems with knowing when things happened. Mm-hmm. We might have gotten it wrong in a few %. Okay. But the construction that Peter's doing, okay, is, I think, the best we could do in the direction you're after.
Okay. Then the other question I had for Rolfo is, many times, this happens in my and other papers as well, that we might cite the same thing in multiple places in the paper. right? Do you have any sense, just as you said, there is a particular section called related work, and clearly that must be more relevant.
Yeah.
Do you have any intuitions, any hypotheses about things that are cited multiple times in a paper? How should I use those to get a good embedding of that paper? Should I weight them more? Should I weight them less? What is the story there?
I think it's more related to the topic, exactly the paper, not. Sometimes when I write a related word, a paper is only talk you a specific task in your paper. The plot each vector about related word paper is most closer to the big model. The central vector represents more your paper.
Okay, and then another thing in the opposite direction, namely, if I cite some paper in my paper, like let's say I cite the paper about the Baum and Petri paper on the EM algorithm, right? Every second paper in my field cites it. It may say nothing about my paper. So in some sense, it's a highly cited paper, it's very important, but I cite it because it's almost a rite of passage, right? So what I'm wondering is whether, you know how with words you have a notion of IDF.
Yeah.
Is there a notion of inverse frequency with these references?
So you can think of prone as kind of like PageRank on steroids.
Mhm.
So PageRank is just the first eigenvector,
Mhm.
and we're getting 280 eigenvectors.
Okay.
And PageRank is also kind of a little like IDF. It's trying to weight things by importance, but if something cites too many things, it's not that useful. It's kind of like a stop word. All right, so if everybody in the world cites the EM algorithm, then that site doesn't really tell you much. So I think this is sort of captured by the spectral clustering inside prone.
Okay. All right. Thanks. Oh, wait, there's one more.
Thank you. So how do you address the fact that the communities, in citations, communities exist, and so cite each other without necessarily going out of this community?
Oh, I just think.
Yeah, so there are going to be lots of mutual admiration societies. That happens, okay. And I think the spectral clustering you can think of as a way that really does identify those communities quite well. And so, you know, you could say it's a form of cheating or not, but actually what I think does happen is in larger communities, it's sort of like larger economic trading blocks. The economy works better in a larger trading block. So you tend to see more citations in larger communities. So if I have a mutual admiration society of two people, I cite my wife cites me, and we're all very happy with one another and nobody else notices. We just don't rack up that many citations because, you know, my family just doesn't publish that many papers. In order to get a lot of citations, you need to influence a large community. And so that kind of cheating, I think, it doesn't really go very far. Yeah. Okay. Ben, go away. Take the pain. Right?
Okay. So yeah, I'm gonna again be talking about production runs. So like running the model that we've been discussing. So like the overview is basically I wanted to optimize the prone algorithm and provide the embeddings to our team and to people in the community to use. And so why would people care about our embeddings? They could use them for like various sorts of websites and other things that have to do with citations and references. So this is the site that's currently live that John put together, John and Ken put together. But it's just like one use case of using our embeddings that we produced to find papers and stuff. So again, like what is prone? Like what is the algorithm that they were talking about? Basically, it's just SVD to extract embeddings from a graph, right? But we have some problems that I've talked about before. But on the northeastern cluster, where we're running these jobs, we're limited to 2 terabytes in one day. So Ken and I have refactored the code a couple times and divided it up to be able to run it within time and space. So yeah, just 2 optimizations, Cython, and changing the data type. So Cython, I talked about this last week, but it's basically just an extension of the Python library to integrate it with C. And I guess like why we've kind of focused on it for this problem is because we couldn't just put it all in PyTorch for reasons that I'll talk about. But this is, I don't know, kind of a good practice with some of the math that we were doing in Prone, and also because we're running it on CPU. But basically, it's not like a translation necessarily to C because the code is still running in Python runtime, but it's not in Python bytecode. So you're able to bypass like the Python virtual machine, which gives you some speed ups. And then yeah, changing the data type is just using less space in these huge embedding matrices, right? Just using less digits for each number. But yeah, a lot of CPUs don't support it, but a lot of the ones that we are running it on do. So what do these optimizations give us? Here's like some pre-optimization graphs for the second step in the Prone algorithm. And then clearly there's some improvements we saved. Oh yeah. Well, okay, so I guess the axes also, the bin is, the x-axis is what percentage of the graph we're using, and then the y-axes are the time and memory, and the dots are observations, and the lines are lines of best fit for those observations. But we found 28% time improvement with our optimizations and a 27% memory improvement, which is pretty significant, and I'll kind of like give perspective on that at the end. And then this graph is just kind of showing like you can think of it as like a histogram that shows like the RAM over the input size on the x-axis, and then the density is just how many bins or how many runs on the graph exhibited these ratios. But you can generally see that the RAM size for the optimized algorithm is around 2 times larger than the input graph, whereas before it was around 3. And it's not like a 50% decrease because not all the matrices in like the libraries that I was calling to take advantage of this smaller data type. So there's definitely some library stuff that I didn't sort through, but it's still pretty significant reduction. And then for the final step in the algorithm, again, you can see the projection or the measured data points and then the lines of best fit. And then again, some pretty significant improvements, a 20% time improvement and a 23% memory improvement. And there's probably a few reasons why it's not as significant as the Chebyshev step in terms of both the improvements. But I haven't like measured them, so I won't get into that. But we do have some like thoughts about why that is. And then yeah, I guess this is kind of like the perspective on like why this matters. So the total compute time that we've spent running these jobs is around like 83 days, right? So any time that we could shave off of that total compute time is significant. And then we've used around 100 terabytes of memory to produce these bins, which is a lot. And without these optimizations, it might not have been feasible to do as much as we did. So I think that's pretty significant. But yeah. Yeah, that's it. That's it. Yeah.
Take questions.
Oh yeah, if anyone has a question.
So Ben, go back to one of any of your graphs with dots, and yeah, maybe this one's good enough.
Yeah.
So one question I had was, so let's say on the left side you're looking at, so okay, first let me make sure I remember. Graph partition means what Shabnam said earlier.
So
40 means that it's 40% of 200 million papers.
Yeah.
So it's whatever, 80 million papers.
Mm-hmm.
Okay, so when you have these dots, let's say you do 40 million and then you want to do 60 million.
Mm-hmm.
Do you start from scratch for the 60?
Yeah.
Because in real life, these things are going to grow with time. And is there anything out there that says seed your computation with the initial estimate? I'm trying to think how this goes. Meaning some kind of incremental way of doing SVD.
I think because of the way that like the prone algorithm works,
Mm-hmm.
it like recomputes it from scratch every time, right? So, like that would change like the dimensions of like the input matrices, right?
Mm-hmm.
Which would again, you'd have to like do like some sort of padding, right? On like I just think that would result in like a fall off in performance probably. But yeah, it definitely does seem like wasteful to recompute it over and over, especially like that's one of the main reasons why like some people on our team wanted to use like graph neural networks, right? Like that's kind of like leading into that. But yeah, we recompute it every time.
Okay. And also, there's not just a question too. I'm sure there are other linear algebra experts in the room.
Actually, Sanjeev, I really did want to work on the incremental problem. We just ran out of time.
Okay.
One of the things that worries me, though, is if you look at the time here,
Yeah.
you can see that it's clearly, the projections are clearly quadratic. There's not going to be a linear time solution, I think.
Okay.
So I think that the bigger the graph is, the harder this is to do.
Mm-hmm.
But in fact, it's like no pain, no gain. There are benefits. They're so that, Metcalfe's law is going to work in. So the bigger graphs have more power, but they're also more expensive. So I don't think there's going to be a linear time approximation of this. On the other hand, you're right. I shouldn't have to start from scratch.
Right.
Okay? So there should be an incremental update story, but it can't be to the point where there'd be a linear time approximation of this, I think.
Right. Okay. Yeah. All I'm thinking is that for inverse things, when you perturb a matrix a little bit, there's a way to look at the inverse as like, the inverse of the original matrix times I plus the increment. Yeah.
Right. There's got to be a good answer.
Somewhere. Okay. Right. And the other question was an easy one, Ben. Are there gaps in the dot simply because you skipped some bins, or is it just that? For some
Because pre-optimization,
Mhm.
we did not run
Okay.
on.
It looks like in the beginning you're running on all of them, and then you started
Yeah.
jumping.
So the early ones are much easier than the later ones.
Of course.
And so what we needed on our machine, we have to sort of make bids for how much time and space you need
Okay.
before you schedule the job. So we were using the early ones to make predictions about the later ones.
Okay.
Okay. Now, so we only ran a couple in order to get the estimates of time and space.
Mm-hmm.
Once we have the estimates, then you made them. Now, can you go to the last chart you had? Yeah, no, there.
Yeah.
So that shows where we're at now, or as where we were very, very recently.
Okay.
So we've done most of the easy ones. Now, this says 80% done, but it's not, because the last bins are much harder than the first ones.
Yeah. Okay. Thanks.
So you get coffee now, and then we get some game.
Okay. All right. Let's do a 15-minute coffee break.
Okay, hi. Oh, that's very loud. Hi, everyone. Welcome back. Let's get started. My name's Abtin. I'm going to be presenting an intrinsic evaluation of text-based document representation models. So, as you might recall from 30 minutes ago, we're the Better Together team. We're looking at text-based representations for scientific documents as well as graph-based representations. For this little presentation, I'm going to be focusing specifically on the text-based methods. So if we want to encode text, we normally have to plug it into some text-based model. And for this, a really commonly used one is BERT. It's a BERT-style model trained on full text from Semantic Scholar. The amount of training data that was used was around 1 million papers. And they described this training data set as 18% being from the computer science domain and 82% being from the broad biomedical domain. And I just want to point out that when they mention full text for scientific documents, that's really just mentioning, we can read that as being English only. Now, I think at the surface, that does kind of make sense because a lot of the scientific literature is written and discussed in English. But as our experiences in recent years show, there might be some value to looking at multiple languages. So BERT is used in Spectre, which was mentioned previously. Now Spectre is a document representation model based on transformers. And we can really just look at it as a post-pre-training alignment of BERT using the citation graph. So we sample triples from the citation graph, and then we use a triplet loss to align their sentence representations. But we encode all these papers with BERT, and so it really is kind of the foundation of this text-based representation model. So our overall goal with this project was to do an intrinsic evaluation of Spectre. And our first hypothesis is that the quality of the Spectre embeddings can really be only as good as the quality of the underlying BERT representations. If the BERT model isn't really able to process the text, the embeddings won't be good and they won't be aligned. It won't really matter. Since BERT is a text-based model, we can use perplexity to intrinsically evaluate how kind of expected a piece of text is to the language model. And so this leads to our second hypothesis, which says that the quality of Spectre embeddings should be correlated to the perplexity of BERT on some text. So once we have this measure of perplexity, how can we use it? We can use it to evaluate how well the model can represent papers from different time periods and different sources. We can find, using this analysis, we can find specific areas where the model can be improved on. And we can also start to make some predictions. For example, how robust is this model going to be to text written after its training date? And related to that question is how variable is our scientific language over time? How much new things will be coming in that we'll have to handle? More formally, we have the following research questions. So perplexity is often reported as a single point. We want to know, does perplexity in this domain vary by time and domain? And if so, what are the potential causes for this variation? And our second research question is, will language models produce high-quality representations for scientific text produced after the model's release? So our experimental setup, as Shabnam mentioned, we have these bins that partition Semantic Scholar into 100 different bins of equal size. And we've sampled 5,000 abstracts from each bin. Now this is a representative sample. We're not just evaluating the model on the data that it's been trained on, we're evaluating on data that it's likely to see in a real world setting. And we're going to calculate a perplexity per bin for multiple models. We do have to do some house cleaning, so we'll do some very basic data cleaning in order to prevent any noise from affecting our results too much, but we don't want to introduce our own biases into the final results. So we're going to filter abstracts with less than 75 characters, and we're also going to filter abstracts out with less than 10 unique characters. Now this just handles some of the really noisy stuff that's just real junk. It's not actual text. One other issue that we have to handle, this perplexity calculation for BERT-style models is not really well defined. So instead, we'll have to use something that's called model scoring instead to calculate a pseudo-perplexity per subword. And so the way this works, let's say I have some sample sentence, Patrick's pickled peppers. I'll tokenize it with the model, and then I'll mask one token, and then calculate the log probability of the model predicting that token that I've masked out using all of the other tokens. I'll do this for every single token in the sequence, getting a set of log probabilities, and I'll sum that up to get a pseudo-log likelihood for the sequence. More formally, for each abstract that we've sampled, we'll calculate a pseudo-log likelihood, and to calculate the pseudo-perplexity for the bin, we'll sum up all the pseudo-log likelihoods, and then normalize by the number of subword tokens in the bin, and this will give us our perplexity, or pseudo-perplexity score. So I'll look at the experimental setup. We got scores for the filtered abstracts, so we tokenized them, and we used a maximum sequence length of 128 subword tokens, and then we did some further filtering. So we discarded anything with more than 64 pad tokens, and we discarded anything with more than 10 unknown tokens. And the results that we got was a pseudo-perplexity plot for each bin, which shows how these scores are changing across time. So this is the results for CyBERT, which I had mentioned earlier, and by looking at it, we definitely can see that there are changes in perplexity across time. In the earlier bins, there's a huge spike. It decreases really rapidly around bin 20, and it rises steadily until it peaks around bin 80. And so another note is that the perplexity is actually relatively smooth when we look locally. So the difference from one bin to the next is relatively small and can likely be predicted. The first kind of intuition we might have is, does this pattern hold when we use different models to evaluate? And so we can compare the perplexities for BERT base and BERT large, and these are all the same architecture and they all elicit the same pattern. And plotting these together, BERT base and BERT large actually have the same vocabulary, and so kind of intuitively BERT large has lower perplexity scores for the same sample. Unfortunately, we can't compare really cleanly with CyBERT for reasons that I'll get into later. Looking at other architectures, namely Roberta, this is a larger model trained for longer, trained on different data. The trend starts to break down. So we don't see this big spike around 80, and so we'll focus on the BERT models. Now, to compare Roberta to BERT, comparison across vocabularies is really tricky because of this normalizing term. The normalizing term is really just the number of subwords in the sample, and this varies across tokenizers. So we can use a count which is more consistent. These are things like words, which we'll use Moses tokenization for, or characters and spaces are more intuitive. So looking at the kind of plot when we use different normalization methods, so for Moses, we can see that the shape is really just the same. It's just more peaky and a little bit higher. A similar story when using spaces, the same shape is preserved. And then for characters as well, the same shape is preserved. The numbers of characters is just much higher, so it kind of flattens it out a little bit. But now with this more consistent normalization, we can actually compare the models a bit more directly. And even in this situation, we see the same pattern. So BERT base performing the worst, CyBERT and BERT large being the best, and Roberta again showing a kind of different trend. So there's definitely some structure that's happening over time. The next question is, what are the potential reasons for this structure? So is this features of the language? Is our writing style or vocabulary use and syntax changing over time? Enough so that it actually affects the model performance? Or is this because of features of the data? So are papers from new sources, which are suddenly added in 1 year, different from the sources that we were using for previous years? Data from some years could be noisy. There are these two kind of competing effects. And so we really need to focus on the data before we can make any claims about the language. Is that a question? Or? Oh, okay. Just trying to interpret for myself. Sure. Okay. So looking first at the data features, we kind of selected two aspects that we thought might be important, those being language and source. So we wanted to stratify the perplexity scores by filtering for source and language. And the reasoning for this is that different sources may have different levels of quality control, which affect the perplexity score, and languages other than English will absolutely have a super large effect on perplexity because it's all effectively unseen. And so as a brief reminder, the sources that contribute to Semantic Scholar are the Microsoft Academic Graph, DOI, and PubMed, PubMed Central, and some other sources which are considerably smaller. And so first we can stratify by source. And in green, we have the perplexities for abstracts which were found from that source, and red is the scores for abstracts not in the source, and black is kind of the original line that we had. And so for PubMed and PubMed Central, the line is low and consistent for papers from PubMed, which make up about 20% of the sample, and for papers not from PubMed, these are really heavily influencing the shape of the perplexity curve. A similar story for DOI, the papers from this source are pretty well expected, and papers not from this source are handled less well. For the other three sources, MAG is just really too big to make any claims about. Almost all the papers are from MAG, and so we can't make any claims about the papers not from it. And on the opposite end, ACL and archive, sources that we might commonly really expect most papers to come from are so small in our sample that we also can't make any claims about them as well. So we'll focus on PubMed and DOI for sources. The other kind of stratification that we did is by language. And so we run a language detection algorithm on the abstracts, and we find that our sample is actually incredibly multilingual. Even in the earliest bin, which dates back to the 1600s up to sometime in, I think, the 1800s, we find languages that span 15, or papers that span 15 different languages. And as we go forward in time, this number is just steadily increasing. It peaks around bin 80 with 35 different languages in a sample of only 5,000 abstracts. So our scientific literature is just incredibly multilingual. And it's not just scientific literature, it's actually electronic scientific literature as well. Just to be clear though, English is still the dominant language. In every bin, English makes up for at least 80% of the abstracts. And so while there are a lot of different paper or languages found in our sample, we want to know how large the effect it is on the overall perplexity. So we can actually look at this in two different ways. First, we'll compare the perplexities of our monolingual model to a multilingual model. And we can also stratify the abstracts by looking at which are English and which are not English. So first, let's use the multilingual model. We'll use BERT-based multilingual or multilingual BERT. Just because it's a similar architecture, and we can see that as we go forward in time and the number of languages increases, remember that peak was around bin 80, all of the monolingual models, so the orange, blue, and green line are all peaking around this time, but multilingual BERT is kind of continuing on its downward trend. Stratifying the perplexity scores for we can also look at kind of the perplexity scores for English versus non-English abstracts and the effect it has both on the monolingual model and the multilingual model. Red being non-English abstracts, it just handles it extremely poorly, whereas for English abstracts, the curve is much more consistent. And we can see that for multilingual BERT on the right, it has far less of an impact on the overall perplexity scores. And so what are the takeaways from this? Our scientific literature is multilingual, and our models, which we use to encode it, absolutely should be too. SciBERT, Spectre, and SciRep-Eval, they all fail the Bender test. So not only are they trained solely on English, which in and of itself is not a bad thing, they fail to mention that they're trained on English, which is kind of a bad assumption. And so if our models are trained on English and our evaluation is only in English, then we're really ignoring a large piece of scientific literature, and we don't really know how our models are going to perform on it. And this really fits into the Better Together story because a citation is a citation regardless of the language. The graph is really invariant to language. So far, we've seen that the structure we've noticed in our perplexities is largely due to the data. The more non-English papers are really having an effect on the English-only models. But we still really want to analyze the features of the languages. So will the languages produce high-quality representations for scientific text produced after its release? To kind of answer this question, we're going to look at perplexities for clean and only English data. And by clean data, I mean PubMed. For multiple reasons, PubMed as a source is just, I think, smaller and better maintained. And the perplexities of a general language model on PubMed are low and consistent, so the language should be fairly clean. So if we plot the perplexities for English PubMed data, it's just flat. Intuitively, this does make sense. This is probably the training data for SciBERT, and the model is really good at handling it. And so we can't really say anything about the language changes over time, but this doesn't really necessarily mean that it doesn't exist. What we'd ideally want to do is train a BERT-like model on some portion of the bins and then extrapolate our perplexities into the future. And that is computationally not feasible for the 6 weeks that we're here, so we'll use other metrics on this sample to make up for it. So as a very simple experiment, we can look at the emergence of new or unknown tokens. So let's consider the unique tokens found in all the bins up to some bin k as our vocabulary, and we'll just count the number of unique unknown tokens which are appearing in future bins. So let's take k to be 20. So the number of unknown tokens up to bin 20 is 0 because they're all in our vocabulary, and we see a sudden spike even in bin 25. And this count of unknown words is increasing, and it's accelerating, actually. And so maybe by training on data up to bin 40, this will be alleviated, but unfortunately, the number in absolute terms of unknown tokens is less, but it follows the same trend. For bin 60, it's the same story, and for bin 80, it's the same story. So the number of absolute unknown words is getting less, but it's still, we're not seeing enough actually to be able to handle the new words that are appearing over time. Of course, this is at the word level. All our models are at the subword level. So we can, again, consider a similar experiment where we're considering all the bins up to some bin k as our training data, and we can train a sentence piece tokenizer. And for this experiment, we can calculate fertility, which is defined as the average number of subwords per word. We can think of this as kind of intuitive. How aggressively are we splitting the words? A high fertility means that we're really aggressively splitting, and the data is really unlikely to have been similar to what's in the training data. And so fertility is also increasing over time. When we train on data only up to bin 20, we still have to aggressively split, or more aggressively split data from the future bins. And if we look at the bins which had more training data, the fertility does get a lot better, but the difference between bins 40, 60, and 80 is a lot less. And so we can kind of make this claim that most of the language is uniform over time. Once we have training data up to bin 40, the fertility is not much different compared to if we had language data up to bin 80. Another metric that we can look is the average proportion of split words. And so fertility was how aggressively we're splitting words. This is a measure of how often we're splitting words. And so it can be kind of considered as another way of looking at the new words which are appearing. And so similar trend as for fertility, it's increasing again. Increasing the training data, similar trend. Now, unfortunately, if we keep the vocabulary size constant, now we're actually splitting words not only in the future, but also the words that we've seen before. So we've kind of reached a capacity for our vocabulary. And so this means that not only will models have to handle new vocabulary words, but the vocabulary size must be consistently increasing to preserve good representations of the text that we're encountering. So just to summarize all the points, the perplexity that we're looking at is predictable from bin to bin, and it is showing a structure across time. We've shown that the scientific literature is multilingual, and our models aren't. This has a huge effect on the perplexity, and the representation for non-Latin script languages is going to be effectively random for anything that's on Semantic Scholar right now. And to answer our first research question, this effect is absolutely varying across time. We've also shown that while the language of the text might be consistent, new terms are going to be constantly appearing, and so our language models will need to be frequently updated to handle the new terms as they come in, regardless of if they use a subword vocabulary. And so this will require both increasing the vocabulary size as well as training for longer on more data. And so just to wrap this up in the Better Together story, I think a scientific paper's text can give really important information. Peter's going to show next that the sentences can give real fine-grained information about what the paper is discussing. But this only really is relevant if we can accurately encode it. And the majority of papers that are out there in our data sets, or in our databases actually, are going to present big challenges towards this encoding. And in most of these cases, the citation graph will be able to fill in the gaps. Cool. Thank you. So I'll pass it on to Peter now. Sure. Yeah. Yeah.
So a lot of the intuitions that I got out of your talk came from those graphs, on which you use the x-axis as your bin number, right? I'm wondering, since the time durations of the bins are not uniform, if there's a simple way. I think there is a simple way. Just take the median year of the bin and just make that year on a linear time axis. I'm wondering if that'll change at least some of the intuitions we get. So for example, in many of the cases where the perplexity or pseudo-perplexity went down abruptly in the beginning and then slowed down, I wonder if they'll become more linear. Because after all, on the left side, it's actually much longer time. So that was one thing I wanted to think about. And the other one was same thing on the right side, where there are too many fluctuations. Those might sort of just look at like a bit more noise because they'll be really close to each other in time and you might see a trend line through them. That was one thought. The other, there's just a comment. The other one was, you mentioned something about vocabularies which I didn't quite catch. So if you could go back to that for a minute. No, this one I got. This one was actually quite nice to know that. Yeah, just stay on that, the OV is growing with time. So that seems to suggest that, no, maybe not this, the one before this, I think. Before or after? The one which has a 0 and then it jumps up. Yeah, this one. So, are you concluding from this that there'll always be a more superlinear increase in OV rates? Is that what it's suggesting?
I think we can definitely conclude that I might not want to make claims about how fast they're coming in, but
Right.
if the amount of papers is doubling every decade or so, and I think we see a very clear kind of rise in the number of out of vocabulary. And it does look faster than linear, but
Is this mostly jargon, or are there actual, well, I guess not new words in the language?
no, so I think it's actually more, I have to look into this, but I think, yeah, so it is the more specific words that are popping up. And I think those are actually kind of the more important words that we want to look into.
Okay, all right.
Yeah, do you want to make a comment?
Actually, yeah, this is a fascinating topic, actually. So type token statistics have been studied since the 50s. And Pierre Zabel, do you remember him?
Yes.
Yeah.
Xerox,
So,
I think.
well, yeah, but before that, he was in Canada in Meteo, so near the Meteo people. So what they were looking for back in the day was a domain, a subdomain that was as boring as the weather.
Mm-hmm.
So the weather was one of the first things that people were successful with machine translation. And I think it's mostly because you can't say much in the weather. And so what he did is he looked at type token statistics across lots of domains. So Susan Armstrong was interested in whether you could use this, translate avalanche reports in Switzerland. It turns out that avalanche reports are far more complicated than the weather. The weather in Canada is very simple compared to avalanches, all right? And they were looking for domains that were as boring as the weather. And so they would look at the rate of, as a number of tokens that come in, you want to see how many different types you've seen. And in every corpus they've looked at, they see that it increases, all right? The number of vocabulary size increases. The intuition many people have is that there's a finite number of words in the language, okay? But in fact, the more text you look at, the bigger the vocabulary is. This is always true. But the slope depends on the domain. So in a really boring domain like the weather, it comes in very slowly. In the Brown corpus, much faster, okay? In this kind of technical writing, it's probably very fast, all right? Because there's a lot of different things you can say. Also, it tends to be on how uniform, homogeneous the collection is. So like the Brown corpus is a balanced corpus, which means it's not homogeneous. All right, the weather's very homogeneous. The news is somewhere in between. Okay, people have looked at this for enormous amounts of stuff, and what I would expect is that all that he's really seeing here is the old type token kinds of reports that everyone has, and the intuition we have that, you know, all you need are a small vocabulary of subwords and we're done, you know, is really just not capturing what's going on.
Okay. Because that led to another follow-up comment. The next set of, or maybe before, you had figures about fertility, right? So I'm wondering if it's worth dividing this into two sets of vocabulary items, tokens which are kind of these new tokens, OVs, versus those that are not. Because I worry sometimes that our subword representations do a terrible job at things they haven't seen.
Yeah.
So it might be more interesting to see. Because, yeah, okay, that's just a comment.
This kind of is a measure of how good the representation is for the words, and so that's why it's following a similar trend as kind of the unknown token. So as time goes forward, more unknown tokens are coming, or representation for
Yeah, but
those
what I'm
tokens.
thinking is it might be worse because you're still keeping the known words. I'm just saying if you just focus on
so
the
this
known
is like
words.
a, yeah.
Because
gotcha.
overall,
Yeah.
like, you know,
Yeah.
all the frequent things are already counted.
Yeah.
They're bringing it down.
Sure.
And then the infrequent ones are pulling it up by only 0.2. So in reality, they might be going up by 5.
Yeah.
Yeah.
And I think those words are most important because I think actually when we're talking about kind of scientific literature, it's those new specific terms that we have trouble representing are actually the most informative.
Right.
They're the most kind of
Okay.
relevant to the paper.
Right. Okay.
Okay. Okay, so I'm going to be talking about the middle part of this kind of Neapolitan ice cream that is the Better Together story, and that is context. So I'm going to cover two types of evaluation of context methods. The first is going to be intrinsic, just looking at the graph, and then the second is going to be a common downstream task in academic document modeling, which is called local citation recommendation. So to start with the intrinsic, we're going to take our graph, our citation graph, and here we're just going to illustrate it with a small subgraph and randomly pick a paper. And we're going to hop around a bunch of times to find a second paper, and then we're going to do a breadth first search to confirm that those two papers are between 1 and 4 hops apart. And we're going to collect a bunch of those. So we're going to collect around 3 million of those, which are between 1 and 4 hops apart. And we're going to have a hypothesis that our models, whether they're text or their context, should be able to discriminate between cases where the papers are 1 hop apart and when they're 2 to 4 hops apart. And the idea is that by looking at this, we can compare models and we can also compare extrapolation. How well can we forecast out from a cumulative training time into the future? And because all the papers are assigned these bins, which Shabnam was talking about, we can assign these pairs of papers connected by a random walk a bin, which is simply the maximum of the two papers. So if we have paper A in bin 80 and paper B in bin 90, that walk's going to be assigned to bin 90. And so given all these walks and the prone cumulative models, we're going to ask how well can they remember from train? That is the case where the maximum bin is lower than the test train split. How well can they predict the future? And actually, can we quantify that? You know, does this get harder as we get further out from the test train split? So before I really get into that, I'm just going to set something up, which is how well Spectre 1 does at this forecasting task over all the bins. So it's doing about 0.71 accuracy at discriminating between 1 hop and 2 to 4 hop, when we just do a simple cosine similarity lookup between the two paper embeddings and try and find the best threshold. Okay, so let's move on to prone. So here we're going to take bin 46, which was chosen pretty much arbitrarily. It's somewhere in the middle of all our trainings. And the story we have here is a scatter plot, and each point represents a single bin. All the walks that are assigned to that bin, how well are we doing at separating the 1 hop and the 2 to 4 hops? And as we see with this line, which is a moving average, we're getting a pretty simple story. Within train, we're doing pretty well at discriminating between the 1 and 2 to 4 hop. Our paper's related, closely related, or only somewhat related, we could say. And then as we forecast into the future, we cross the test train split, we do worse. As we go further out, we do even worse. So it's kind of like short-range forecasting is going to be easier than long-range forecasting.
And the chance should be 50%?
It's a little bit biased, so the chance of it being 1 hop is 0.3. So I think that's going to mean that random chance is about 0.6. Okay. You're right, I probably should have included that on the plots. And here's the full picture. I showed a zoom in. If you were very observant, you might have noticed I only went between bin 20 and 80. That's because there's noise in bin 0, very early papers, and also very recent papers. The metadata is kind of not settled yet. And we can generalize this. So because Ben has provided so many trained cumulative prone models, we can actually look at the prone models for every case. And so in the bottom left, we have that plot I just showed before with the scatter removed and just this moving average. And in the top left, we see something similar for when we train up to bin 26. Now, what I've done is I've kind of rotated all of those, so we're looking vertically down at them and plotted the height as a heat map. And just on this leading diagonal, which is a dark spot, so I put the test train split. And we kind of see what we'd expect to see, which is predicting inside the training split is easy. And then forecasting out is hard, and it gets harder. But we're also going to see some interesting phenomena at the extremes. So for the really early bins, we kind of do badly in the train set and we do badly in the test set, but it's consistent. So we're getting a flat line as we're forecasting out, but if you look, the reason that's happening is because our performance is around 0.62. And with the really good models, we know everything. We've seen it in train, so we can remember it. Oh yeah, Ken would like me to make the point that this top left graph, where we've only got about 4 million papers in training, is much more consistent with the kind of scale of previous document evaluation tasks. So these phenomena we're observing, where we're really getting these benefits of scale, we need to have about 50 million papers, and I'll have a plot later on that's going to show that. And because these bins are about 2 million papers each, we're only really getting those effects at about bin 30. Yeah, so here we can look at training size versus forecastability. So this is the question of how much do I kind of need to have in my training set before I can consistently forecast into future bins. So this is looking at the average forecastability given the training bin size, which you could think of as the kind of average color to the right of the leading diagonal given the previous context in training size. And what we're seeing here is we start off pretty badly, and then at about bin 17, we cross over and we get better than Spectre. So this is kind of empirically answering the Metcalfe's law point, which is when we hit 30 million papers, we start to do better than Spectre, and then we carry on getting gains all the way up to about 60 million. And this is the other thing we can look at here, which is how much easier is short-range forecasting than long-range forecasting. So for every model, we can average kind of 1 step out, 2 step out, 3 steps out, or bins out, I should say, and how accurate are we at that. And we see this pretty intuitive pattern where forecasting 1 bin out is easy, and actually it stays consistent for quite a long way out, and then we start to see a real drop-off at about 40, 50 bins, and that becomes pretty pronounced once we go all the other way to the other end of the training graph and we're approaching kind of random chance. Okay, and here comes the better together story, which I know you've all been waiting for. So with the blue line we have prone for 46, which I've already shown. For the green line we have Spectre, and then for the red line we have a setting where we're using both prone and Spectre. And I'm just going to swap to a plot where we don't have the scatters because it's a bit cleaner. So what's this showing? This is showing that for within the training set, prone is best memorizing those links, which is perhaps unsurprising because it's being trained on them. But when we start forecasting, it looks like it turns out the best strategy is to use prone when we have it, and then to use this red strategy, which is prone, what we call prone plus Spectre. And what we do here is if we can form a prone embedding, we do, using the strategy Rodolfo was talking about, where we take the average of the paper's references to form the embedding. And if we can't find any references, we use Spectre. So use the references when you have them. When you don't have them, use the text. Okay, so the conclusions from the intrinsic evaluation are that context works. The prone model is very effective for modeling document links. But you need a large collection to get that really going. And we're talking about 50 million to reach the convergence point. So if you want to forecast well, if you want to do well at this modeling, you need a lot of papers before Metcalfe's law really kicks in. And at lower scales, even at about 30 million, text is better. Forecasting gets harder as we move further out from the training set. We kind of know this. Short-range forecasting is easier than long-range forecasting, as I've already said. But this has an interesting implication in that I think people often assume that models are kind of one and done. You can upload them and always use them. But certainly in this domain, our models are always rotting, and we need to be aware of how well they're going to forecast and have some strategy for updating them at a certain point. And finally, text is a solid baseline system, and we can think of it as a fallback to further improve performance from context models. So that's really a better together story. Okay, now I'm going to move on to the second part, which is extrinsic evaluation, which is a task called local citation recommendation. So we have this higher level task called citation recommendation, which is asking the question, what should I cite in my paper? And local citation recommendation is, I've just written a sentence within my document, what should I cite at this point? It's a pretty established task. We've got papers at ACL on it. There's many data sets. And they tend to be fairly small, certainly in the context of what we've been doing. So full text peer read is 10K samples, ref series 3 million. And we've created our own task from the Semantic Scholar data, which has full text, which they call S2Awk, which is around 12 million papers. Every citing sentence within those, and there are about 400 million, is a data point. So we're going from 12 million papers to up to any of the papers in Semantic Scholar can be targets. So we've got this 12 million to 200 million mapping with 400 million samples. Okay, so what does this task really look like? So let's take a paper, the Deep Walk paper. It's a paper with a title and an abstract. It has a bunch of sentences. Some of them have references, so we would call those citing sentences because they have citations at the end. We're going to take those and map those IDs into semantic scholar IDs, which are going to become the targets. And the rest of the document is fair game as context. In the classic formulation of this task, generally the title, the abstract, and the sentence are used as context, and the model's asked to produce the references. In our version of it, we're also considering something where you use the other references as context. So that's becoming a little more like what Rodolfo was doing with his related work hypothesis. So what methods do we try out? Okay, so for text-based search, we use the pretty traditional title and abstract method in the bottom left. So we take the embeddings of the title and abstract and try and match to other titles and abstracts with no accounting for the citing sentence at all. So this is a really kind of simple baseline. Then we also try using the titles and the citing sentence and matching that to the titles and abstracts of target papers. And then finally, we do something a bit more interesting, which is matching the citing sentences to other document citing sentences. So this is a bit like if I'm writing a reference, can I find other references to this paper which other people have written and try and match those directly and then take the shared target. And that's kind of interesting because you have cases like this, like Alan Turing's paper on computable numbers, where he introduced the Turing machines, but he doesn't actually use that in his title or anywhere in the document. So you can only get signals like that by using the citing sentences. And then for reference-based search, we're using prone embeddings, but we use three methods. So we use the source, which is just to take the prone embedding of the source document directly, again, not using any text. The centroid method, which is, again, similar to what Rodolfo introduced, where we take the average of the prone embeddings of all the other references in the document. And this is kind of saying, I can tell what you're going to cite by looking at all the other things you've cited. And then we use something called the weighted centroid method, where we weight the prone embeddings of other references by how far away they are in the text of the document. And here are the results in terms of recall at 100. We've got the recall at other bins, but we'll just start with this. So what do we find? We find that the citing sentences is the best text-based method. So about 12% of the time, 11% of the time, sorry, that's retrieving the correct paper in the top 100, which sounds pretty weak, but we are dealing with 200 million candidate papers here. Both the other more traditional text-based methods that perform very poorly. Yeah, so using the citing sentences in a way that the models are not really designed, basically is garbage. And trying to match on titles and abstracts is just not good enough either. Moving to prone, we get three very strong results, but we do find, interestingly, that the best method is this centroid weighted method, which again is suggesting that there is useful information in terms of where references are in the document, which is more evidence, I think, for what Rodolfo was presenting. And now moving to the recalls at 1, 10, 100, and 1,000, we get quite an interesting story where as Abtine mentioned, the citing sentences themselves are a very strong signal for high up in the retrieval list. If all you care about is recall at 1 or recall at 10, then the citing sentences are going to get the job done best. But there seems to be some limit to this. They're going to hit against it pretty quickly, and expanding the recall list isn't going to help. They're either there or they're not. And we could look at whether that's because the matching isn't perfect or because actually there just aren't enough referencing sentences to have full coverage. I suspect it's more to do with that. But the prone methods are pretty robust in terms of they continue giving you better answers as you look down the retrieval list. Okay, conclusions. So reference recommendation, local citation recommendation at the 200 million paper scale is possible, but it's hard. Citing sentences are a great signal, but they're incomplete. We get the information quickly, and then nothing more. As we move from recall at 10 to recall at 100, we're getting kind of 1% increase. As the intrinsic evaluation I presented before showed, prone is very capable at link prediction, and it's less strong initially than the citing sentences, but as you continue down the retrieval list, it's adding more and more. So we're adding kind of 13% and then another 10% as we go to recall at 100 and recall at 1,000. And title and abstracts alone are pretty weak. And future work would obviously be combining the citing sentences to get these initial gains and then the prone system as some kind of fallback. So again, another better together story to be made here, I think. Okay, cool. I'm going to hand over to Melissa now. Oh, questions?
Questions? Go for it, Sanjay.
Okay. So one was, let's go to the picture where you showed that if you use the first 3 bins, it's terrible across the board. If you use the last one, of course, everything is seen in training, so it looks great. So one worry I would have in taking this to the bank would be that there is other evidence elsewhere that the really early bins are problematic.
Mm-hmm.
So would you consider, maybe you should consider an experiment where you throw away the first 20 bins altogether and then take 21, 22, 23 as your starting point and then repeat this and then again throw away the first 20 and do the full embedding on just the last 80 or something. The reason is I'm worried that there's too much noise in the papers that are like 100 years old.
Yeah, I'm kind of interested in that as well. And what we're seeing here is that once we hit 30 training bins, we're kind of not getting much more gain in terms of forecastability.
Right.
And to me, that's either implying that we've reached some expressive limit of the prone method or that actually 30 bins before is just so different from whatever the literature is, it's not helpful.
Right.
So what we could do to test that would be to pick one test train split, say bin 80, and then train just on bin 80 or bin 79 to 80 and step backwards that way. And that way you kind of wouldn't back into these problematic bins.
All right. Okay. I was just thinking of removing the first few bins so that that noise issue goes away. Just,
Yeah, that could also work. But I'm going to imagine that those are going to be kind of drowned out by the later papers as we add more bins.
Okay. Then I had another question which is a little further out. When you're looking at the citing sentences, and I think you reinforced Rodolfo's story that if I have a new paper, let's say I'm writing one, and then I need to use an embedding for that paper to figure out other things, then the centroid method works well. And the weighted centroid is a variation on it. But in the experiments that you did, you had, let's go to that picture where you had the example of, exactly, one of these, right? So it's basically all or nothing, meaning you have the sentence, you want all the references for it, and you check recall to see how many of them you got.
Yeah.
Right? In real life, it's often incremental, right? I might think of one reference and then put it in and say, what else do I need? Do a bit of a research. Oh, I found this one. I'm wondering if there's an incremental version of this task where you say, given the citing sentence, given these references, let's find, the missing references, let's find a few, let a human pick the best one, put it in there. Now you have some idea what this sentence is trying to cite, and then use that plus this. So in other words, I'm thinking of what a real life task might look like. You're not going to just do it once. You're going to, do something and say, okay, what else am I missing? Who else should I be citing, or what else is relevant? So I'm wondering if there's an incremental version of this task where you try to, what I'm thinking specifically is that if there are 4 citations, like in input 2 over there, these 4 are, actually, there are only 2 citations, I suppose. Yeah, okay. So let's take the example where that, I'll look at the references 15 and 37 over here, right, in the left side. So once I know 57, is it easier to find 15? Is it easier to find 37?
Sure, so we do a fairly minimal change to the data set and just move one of these outputs to the input is kind of what you're saying.
Right. It's almost like saying there's the task where you to find all the references, and there's a task where given one reference, find the others that I might be missing.
Absolutely, and I think that would be a much easier task, but also an interesting one to study.
Yeah. I'm just thinking that might be more like what people want in real life.
Okay.
Okay. Other questions?
I'm wondering, so I have this intuition that some citing sentences are like the Turing machine case, where it's very obvious what I'm citing. And then there'd be other citing sentences that are pretty, useless, like for more information on this topic, see blah, blah, where they don't even say what this topic is. And I think that might be what's going on here, that in some of the citing sentences, the clue is really very useful and it's great. In others, it's kind of hopeless, and you better use something else like prone. Yeah.
Yeah, absolutely. Okay.
All right, so now I'll present some experiments related to another task, the task of document time period prediction. And so an overview of this task, we're given a single query paper, and from that query paper, we want to predict the time period from which it came from, or the time bin. And so for each paper, we have access to information such as the embeddings, specifically 4 different ones, the specters, vector2, cite, NCL, and prone. The references of that query paper, which we can get from Semantic Scholar, similar documents to each query paper, as well as a map of the year to the bin. And then some motivation for this task, we can try to understand the contribution of embedding types and nearest neighbors on predicting information about the query paper, and also detect missing or incorrect data, which happens surprisingly often in the data set. And it also serves as a proxy for other tasks like venue prediction, field of study, reviewer matching, and collaborator search. And some of those tasks might have a more clear, practical value. And so an overview of the experiments, I start out with a baseline using the references. So for this one, from the Semantic Scholar API, we can get the time of all the references of the query paper. And then we take the most recent bin of those references. And for the similar paper, as Ken mentioned earlier, we have an embedding of all the papers. That's dimension n by k, where n is the number of papers, so about 200 million. And then k is number of hidden dimensions. And then we can calculate the similarity pairwise of all the documents using the m times m transpose. And that's all cosine similarity. And then we also have the direct embeddings of each paper. So prone is based on citations, and the 3 other ones are text-based. And finally, we try combinations, which is pairs of the embeddings. So overview of the data. So the data comes from bigrams that contain triplets, where the first column is cosine similarity. The second one are the list of query papers, and the third one is a list of similar papers for each query paper. And each query paper is listed as many times as the number of similar papers. So after some initial experiments, we can see on the graph to the left, it's a graph of the count of pairs of papers, where the first paper in the pair, so on the x-axis, it's the bin of the on the x-axis is the bin of the first paper, and the y-axis is the bin of the second paper. And we can see that it's much lighter along the main diagonal and fades off as the offset increases. And this indicates that papers that are similar to each other tend to be closer in time. And we see something similar with the graph on the right. And this graph is constructed by taking a sum along the diagonals. So a 0 offset would correspond to the main diagonal, and then as we go to the right side, that would be a positive offset, and then down here would be a negative offset. And we can see that the rate of decrease here indicates that the ones that are more similar tend to be also closer in time. And so for the baseline, we're just using the most recent reference. So basically we have our query paper, we get the list of references from Semantic Scholar, we take the max of the bin numbers. And then I also tried the bin +1 and +2, and we can see that for the same bin or the bin +1, we get about 18% and 20% accuracy just from that. And then if we take the cumulative accuracy from just the same bin +1 or +2, we get about 50%, which indicates that for about 50% of the papers, we can get it just from taking, it's within 2 of the most recent references bin. So based on the charts from earlier, it suggested that similar papers tend to be close in time. So for this experiment, I tried using the similar papers to each query paper. So given a query paper, we have a list of the similar papers. And for each similar paper, we have access to the corpus ID and the cosine similarity. So then we can rank the similar papers by the cosine similarity and then take the top K. And for the K values we considered were top 10, top 5, and top 1. And the results are shown here. And it does a lot better than random, which would be around 1%, but not very well. So the top was the top 10, about 7.5%. And then next we considered embeddings. So for each of the 4 embeddings we have access to, and for each query paper we can calculate the vectors and then use those. And using the embeddings themselves we get a lot better results. We get the best results for prone, followed by Spectre, and Spectre 2, and then ScienceCL with very low. And then noticing that Spectre and prone both do very well, now we experiment with combining the embeddings. So for each pairing of 2 of the embedding types, excluding when they're the same, we take the vector for the first embedding and second embedding and concatenate them together. So we end up with a vector that's a lot longer, and we can see from the results that in general we tend to get better results when prone is included. So prone is the only embedding type that's based on the citations. So this indicates that adding the ones that are based on text and the ones that are based on citation leads to the best results. And the best was prone plus Spectre 1. And then this is a summary of all the results from the 4 main different methods. And then for next steps, we could consider other features like instead of just considering the max of the references, also consider the min, max, median of the references or the distribution of the time bins of the references. Could also improve data pre-processing, especially with missing vectors, trying other model types, extending to other related tasks like venue prediction, field of study, reviewer matching, and collaborator search. So recently, AI2 released Bridger, which basically, given an author, can suggest other authors that are similar based on task and or method. And some description of the other tasks. So for venue prediction, given a paper, predict the publication venue. And the value of this could be a researcher who wants to determine which venue to submit to. Field of study, determining the topic of the paper. Reviewer matching, come up with more effective reviewer paper matchings. And then collaborator search, given an author, recommend potential authors to work with. We could consider the similarity of papers from the different authors. And then now Sandeep will talk about GNNs. Oh.
Hi. So I'll be discussing the GNN approach, which is another way to combine the text and the citations. So a brief outline of how I'm going to proceed is with a background of GNN training and inference, and then the challenges and solutions we had to the challenges we had to handle when we scaled to this extreme data set, and a summary of our evaluations and what we plan to do in the future. Okay, so just to bring back the old question, how to combine text and context. So we have prone, which is one approach which our teammates have been studying. And the second approach I want to consider over here is a graph neural network approach, which is a deep encoding approach. The advantage of this is that it is an end-to-end training capability which combines text and citations from the start. And this also gives us some advantages of inductive learning capabilities. So graph neural networks are similar to convolutional deep networks, except that the graph is going to get encoded into a single dimension vector, similar to how images are encoded. The citation graph, and which is encoded with the GNN combined with the node features, present a new embedding which can be used for future tasks like link prediction. The problem, one of the challenges we have is that this graph is extremely large, so we had to resort to something called mini batch based GNN training. In this particular context, we extract a sample of the subgraph that we require, and then we pass in the text features which are aggregated for every neighborhood. So the 2-hop neighbors send the information to the 1-hop neighbors, and the 1-hop neighbors give the final encoding to the target vertex. So this is the graph every layer of aggregation is termed as a graph convolution, and this is like an end-to-end way by which we can combine both the text and the citations, because the text represents the information that is being flown, and citations direct the direction in which the information is going to get aggregated. So that being the GNN training setup, we have two settings that we primarily consider in this particular case. The one setting is called the transductive setting. In this particular setting, we have access to only the blue edges during training time, and we are trying to predict the green edges as our target. But the thing is that we already have seen some of the neighbors of node 1 and 5, even though we are trying to predict them. So this gives us a little more information. And the next setting is like an inductive setting where for the nodes that we are trying to predict, over here, which is shown by the red edges that we are trying to predict, we haven't seen any of these edges or their neighbors at all during training time. This corresponds to a setting where a new paper has arrived and we basically have not seen this paper at all during the test time, during the training time. Whereas in the transductive setting, it is like we already know what are the papers we are trying to predict on, and we are trying to see if there's a missing information, and we are trying to learn more. So in these two particular settings, one advantage that GNN has is that the inference part becomes very, very simple because of the approach I've started with, which is the mini batch based approach. All you have to do is start with a subgraph sample, and you flow that subgraph in through your GNN encoder and get the encodings for the target paper and its possible representations. Now, coming to some of the challenges that we had in this particular scenario is that the scale of the graph is extremely large because, as my colleagues pointed out, the graph is ever growing and people like to publish, I guess. The size of the graph topology is around 40 gigabytes, and the feature data goes to around like 300 gigabytes. But graph neural networks, like deep neural networks, rely heavily on the GPU to do most of the heavy lifting, and 180 gigabytes, around 300 gigabytes of data breaks that memory barrier. So we had to come up with a novel graph partitioning algorithm which decreases the memory load, and along with some tricks of using hybrid GPU memory. The other problem with the other challenge we had is that the data set is very messy, and graph neural networks require some notion of uniformity. So when you have the data being messy in this particular example is a paper with incomplete information without any text. So in order to handle that particular problem, we have proposed a solution of a learnable embedding, which is like a placeholder, which we learned during training time. And yeah, so this, as I mentioned, is the problem with the graph topology. It's insane. The graph topology being very, very high. So we use sampling to decrease the active memory that we require. And yeah, and now how do we use this partitioning approach that we come up with? So we are familiar with this particular training loop, which is the heart of all the deep learning that we did, except that this is a more, the first point I'd like to highlight is that we are only going to focus at one partition at a time, restricting ourselves to for every going one partition at a time and sampling only within that partitioning at a time. So that also adds a little bit of, allows us some advantage that we can break this training pipeline into multiple stages, and extending upon the work of some of my colleagues, we can add some checkpointing and break this pipe, like how we did in the prone optimization where we broke it into 3 stages. We can do something similar where each partition represents one particular stage of training. And then that brings us to another question: what is a good partition? The consequence of this training algorithm is that we are throwing out a lot of information that is cross partitions, and we have to minimize that. the solution to this is that, well, do better graph partitioning. And we can point out that graph partitioning is a very, very well-studied problem and decades of research. Problem is that it takes forever to do graph partitioning, and it takes an extremely large amount of memory, and even a standard matrix partitioning cannot handle something like this unless you have a supercomputer or you have massively parallelized it. So a quick and dirty trick I came up with is that we rely on data heuristics. It's the fact that papers which get published typically cite papers in the same year, in the sense that papers published in 2020 rarely cite a paper in 90s, right? They will have some sort of time notion which adds to the clustering capabilities. So we start extending on the ideas of my colleagues where they did some binning. I sort the papers by bin and accumulate papers in a set of bins into a basket and term each basket as a partition. And surprisingly, I got very good degree, and the partitions highly resemble the graph. The next solution about getting over the graph memory, the GPU memory requirement is using unified virtual addressing. This is, in the left side you see without UVA, where each GPU's memory is limited to itself. On the right side you see that the GPU is able to seamlessly access the host memory. And we use this particular trick to allow the GPU kernels to have access to the large disk space, which is around 500 GB. And lastly, the missing node features. In the first diagram, we showed how the mini batch sample is being handled. In scenarios where there's a missing feature, we created this learnable embedding, and this learnable embedding has a gradient. And when we learn from our loss function, we are able to learn some sort of a placeholder. And this idea is like is borrowed from the fact that when papers are missing, they might be missing for the same reason. And finally, some statistics of our data set is that we trained on, in this particular case, I've trained on like a graph with 20 million nodes and and around 1.3 billion edges, out of which, it's 80 million nodes, out of which 20 million are without text and 60 million are with text. So that's like around 25% of the papers have missing information. And in the inductive setting, the number of papers that are available increases because I'm seeing more papers. It's not that I'm predicting information for papers I've already seen during training time. And finally, the accuracy, the mean reciprocal rank that we have is, we can see that papers with text perform better in all cases, and then papers without text. That's expected, I guess, because we have more information and we're able to use it. But still, there is a substantial gap between them, and how to bridge that gap would be an interesting question to answer. And finally, the deliverables that I plan to deliver is that the GNN model that I've trained, I plan to share it and open source it, along with the embeddings, which I hope will present like an alternative to the already ones collected and can be used alongside with it. And future work, which I hope to cover after the workshop, would be GNNs allow us to capture a lot of other signals, such as direction, because they can be trained to be heterogeneous, and other tricks like using citing sentences as edge features, and expand on the capabilities of graph neural networks. Yeah. That's it.
Yeah. Are there questions for anybody so far?
So Sandeep, I did have a question. So let's go back to this notion of partitioning the graph. You had an assumption where you said, I can do this heuristic sampling, assuming that papers cite other papers near them. So what I'm wondering is whether this has a tendency to systematically undersample good papers that, let's say, stand the test of time. They get cited long after they're published, and so papers long in the future will cite them.
That's actually not going. Can you repeat this question again?
Yeah, so you said that when you create your partitions, what you want is you want the partitions to sort of be, imagine that if the original citation graph truly had unconnected subgraphs, then those would be a natural partition, correct?
Yeah.
But given that they are connected all over, now you're thinking, how do I get it's almost like a min cuts kind of problem. I don't know whether that's what that Metis algorithm.
This is a min cut.
Okay, I didn't know that by name. Okay, so you're kind of looking for a min cuts, but then there might be nodes in the graph which have high degree in the sense that not only are they connected to many papers, but that their degree has a long temporal span, meaning the nodes they touch span a very long period of time. So I would call those papers like, things that stood the test of time. Many papers years later. So wouldn't this systematically undersample them?
No, it won't. Because that will happen if you are doing node partitioning, but we are not just doing node partitioning. So the thing is, so let's say that when I create my partitions, so let's say there's a paper that got published in 2020. When I put it in a partition, I also put all the papers that it has cited. So if there is a paper that is progressively being cited by everybody, there would be somebody else in this bin who cited that, and because of that reason, this partition will include that particular paper. So these partitions are overlapping. So partitions contain nodes. These are not.
So they're not partitions in the sense of disjoint partition.
They are not disjoint partitions. These are edge partitions because the edges are disjoint. When your edges are disjoint, the nodes can overlap, right? So that's the answer to that.
Okay, so these are not node disjoint, they're edge disjoint.
They're edge disjoint.
All right, okay.
But that still gives us enough leeway. So this means the information I throw away is not direct. I do throw away some information, but it's never one-hop information.
Yeah,
it's
understood.
always two-hop information, which I'm trying to assume that it's not that bad.
That's okay, and you could always extend it to say, let's take everything that's two hops.
Yeah.
It'll then give you bigger subgraphs.
Yes.
But okay. The other thing is, again, my ignorance. You mentioned something about GPU memory or something.
Yeah.
Yeah, I don't know this business. What is this UVA? Can you just say a bit more?
Yeah, sure. So, so one of the biggest, I guess, worries people had when I was proposing the GNN idea is that you will need GPU memory, and GPU memory is limited, and because GNNs generally have GPU-based kernels, how are you going to get over this memory requirement? So this is unified memory, which basically means that a GPU kernel can access not only its global memory, but also CPU memory and other GPUs memory. So that technique basically has a little bit of more housekeeping, because the memory you create has to be mapped into everybody else, because it's virtual memory, right? So the page table has to be mapped on every particular GPU. So using this particular technique, after you do the housekeeping, which is create the memory, pin the memory, and share the page table and everything, the GPU gets the ability wherein a GPU kernel is able to issue memory requests not only to the global memory, which is local to it, from the perspective of the other GPU or the CPU, but it's also able to access the RAM memory. And that basically means that it might be slower, but you still are getting the parallelizability.
Okay.
Yeah.
And so, I mean, there's no free lunch, right? So what slows this down? I mean, what's the cost to pay?
It's going to be slower. There's no free lunch, and accessing global memory is going to be faster always. And when you do this particular trick, you still have to you're still going to be bound have a latency time. But just because GPUs have a lot of parallelizability, you can hide that latency. So the cost you have is that it's not going to be as good, but you can pull it off because GPUs inherently hide latency under parallelization.
Actually, just following on the same problem. So in this situation, can you still rely on optimization like coalesce memory access, so you can load multiple times?
Oh yeah, you can.
Okay,
and
so that's good. Then you can still benefit from
all that benefits really. The cacheability and locality, all are still applicable. Yes.
Then that's cool. Thank you.
Yes.
We have a question online. I've already answered the question. Yeah, so we have a question online. I think for the sake of the audience here, I can repeat the question. So how about the missing value placeholders? Do you use one learnable vector for the nodes, or use multiple learnable vectors?
I use one learnable vector, but it would be interesting to see if we can have multiple.
That's exactly what I replied. Great answer.
Well, I'm a student. I'm supposed to represent my advisor.
Pay no attention to, right?
That's all. Thank you.
So I'm going to wrap up now. Oh, no, I'm not going to wrap up from there.
Yeah, from here, I guess.
There. I'm wrapping up now. We're almost done. I think we're supposed to be done at 4:30, and I think we'll do just fine. And if there are any questions, like if there was something we went through too fast or something, you can just, request that we go through it. So here's the agenda. This is what we've done. We've done pretty much all that we said we were going to do. The first half, we constructed the bins, and that made 100 times more work because we had 100 bins. Actually, it's not quite like that. It's worse because each bin includes all the others. So the last bin is 99% of the work, and the one before that was 98% of the work, and you sum that series, and it's a lot of work. So that was the pain on Ben's side of the ledger. But what that made it possible to do are a lot of the experiments on the right. The perplexity experiments, what Peter did, and Melissa, and many of those things. So just to recap, just in case you forgot, we're talking about text and context. There are a lot of standard embeddings for text. There's standard embeddings for context, or at least we constructed these, where all of these things are available on the GitHub. You can download all of it, at least through Globus. A lot of the embeddings are way too big for GitHub, but from the GitHub, there are pointers to Globus, and you can download a lot of these things. But they are big. Now, the text stuff tends to be the author's perspective, and the context is the audience perspective. I think Sanjeev covered that pretty well. One of the things, of course, we keep trying to emphasize is missing values. We have missing values everywhere you look. This picture of these circles only covers like 2/3 of the picture, because there's another third that doesn't have either abstracts or links. And one of the simple better together stories is use what you have. So if you have abstracts, use them. If you have links, use them. That's a great way forward. Now, the other part of the better together story is a little more complicated, which is that when the graphs are really tiny, then the text tends to outperform the links. And when the graphs are really large, then Metcalfe's law starts mattering, and the links sort of outperform the text. And this trade-off is sort of non-obvious, and you're not going to get there by looking at a tiny benchmark, which is what we typically do. The tiny benchmarks tend to conclude that text is better than links because it is in the tiny region, but that doesn't generalize. Another thing that was sort of in Peter's thing is that the trade-off here not only depends on the size of the graph, but it also depends on how far into the future you want to forecast. That's sort of interesting. So here we could take a look at Peter's graph again. And one thing I want to point out is that in general, the context is better than the text. So at that point, the blue line is just well above the green line. One thing I want to point out here is that for prone, we did the heavy lifting that Ben described. We trained prone on not all, but 80% of those bins. So we got most of those bins. In Spectre, we didn't retrain Spectre for everything. We just took whatever the Spectre models are and applied it to everything. And those models were trained on most of this stuff. But even though they're testing on the training set, they're still underperforming. Now we hope to, we were close to having Spectre on the bins, but we don't have that yet. Now, the ensembles are generally better than either model by itself. And that's where the red line sort of outperforms all the others, especially at the right. And what that's saying is that the text is most helpful when the links aren't working so well. And that would be trying to do really long-term forecasting. That's where the ensembling really helps. So that it's not only you're in there. Now, and one of the things I also want to say is a lot of the benchmarks are really talking about the stuff at the left-hand edge. I think that works here. In here, a lot of the benchmarks are talking about only a couple million papers. And in that region is where it's really hard to say anything. It's the I think your real lessons you learn are when you're looking at large stuff. And the trade-offs are a kind of an interesting picture, but the trade-offs depend on how much training you've got and how much forecasting you're trying to do. Okay. I guess I did say GitHub, didn't I? All right, please take a look at it. All these slides are there, there's also this website that's up there too. And there's the website again. And I put all these things, and now that it's being live streamed, all those QR codes are up there so that the QR codes either point to the website or the web page. We want to talk about deliverables. When I talked about these deliverables before, but a lot of them were forward pointers to things that have now been explained. So, well, the GitHub, it's massive. It needs editing, I agree. It's sort of it was a way for the team to share things amongst itself. And we need to sort of digest the products and turn it into publishable papers and maybe lots of little pieces. But anyway, there's a lot of stuff up there. The web server puts out recommendations, and it will get better over time as well. But it does already kind of give a suggestion. You could input a document and it would suggest some more. Resources. We have all the data behind the web server and much more there. So we have all these citation graphs we were talking about, embeddings for all the bins, as well as embeddings for Spectre 1, Spectre 2, SciNCL, Prone. We also have link BERT. There's a lot of stuff I didn't even put here. It's all there. We have the file that Melissa was talking about, the pairs of corpus IDs with large cosines by all of these embeddings. And we also have that for many of the bins. And I didn't mention all the indexes for the approximate nearest neighbors. And I know I raced through the approximate nearest neighbors stuff. I'm happy to talk about that if there's any questions. As for the evaluations, so there were a bunch of evaluations that we mentioned here. Rodolfo and Peter and Abtin, they all have things. And those will all turn into standard benchmarks that we'll share and distribute. And as we say, these I think are more interesting than a lot of the standard benchmarks that are out there because they push you to think about not only a single figure of merit as to how you're doing on one data point, but they start to push this question of how well can you do forecasting and how well can you predict with how little training material or how much. And I think that the conclusions you come to depend a lot on these scale questions and also the forecasting questions. And I think that trying to answer these things like what's the best method based on one data point, especially if that data point is based on a very small sample, just doesn't really work given Metcalfe's law. So that's pretty much it. Thank you.
Questions? So Ken, I have one, and then I also have a request if it can be met.
Sure.
So first the question or a comment. Go to your very last slide, the one where you were reprising Peter's red, green, blue graph. I had not picked up on a subtlety, which I do now, and I'm wondering what to do. I think there's just PowerPoint getting you the images.
What's happening? Is PowerPoint just struggling? Why is it so awful? Oh, because it's PowerPoint. All right. Huh?
Okay, Gregor is on his way. He will fix it.
Please get me out of here. All right.
Okay, and while he's fixing that, let me make a request.
Sure.
You mentioned something about a website.
Yes.
So do you think we could do a demo?
Yeah, I guess we can try.
What I'm
Let's give
thinking
it a
is
shot.
maybe first you show us 1 or 2 papers and that you know will give you good answers.
Yeah, all
and
right.
then maybe someone in the audience will think of a paper and we'll see what we find for that.
Okay, so let's. Gregor's almost done with the first request, I
Yeah.
think.
So,
All right.
yeah, go to the very end and pick Peter's graph. So this was just a sort of, I would just say the cautious part of me says, when you get results, wait a few weeks before you believe them. So yeah, go to that one. So what I'm worried about over here, I had not realized that the blue curve, which involves the network embeddings,
Yes.
was trained only up to the dotted line. So really what is to its left are papers and its training data.
Yes, of
and to
course.
the right data.
Right, so
Okay.
it does better on the
Right.
training set than on the.
The green one, you said actually is trained on everything.
Yes.
So what I'm wondering is if the green one's trained only on the part to the left of the dotted line.
Would it do better?
No. Maybe it'll start going down as well.
Oh, it would, sure.
And then I'm wondering whether the interpolation will then always sit in between.
Oh.
And it won't be better.
Well, yeah. So, well, we're now speculating.
No, I know. That's what I'm saying. Caution. Like,
I
before-
actually have, all right, so let me be very undiplomatic here for a minute. So the Spectre is fine-tuned version of CyBERT with, and this is the part where I'm going to be undiplomatic, it's got an extremely tiny training set, like, only, I think, 1 million papers, all right? And then even worse, there's a huge overlap between the test and train on CyBERT. So they report massively great results on the evaluation. I'm sorry, test and train on Spectre. But there's like a 40% overlap between test and train in that collection. Mm-hmm. So I actually believe that the green curve is really suffering because it's completely undertrained. It has, it's not only, it's just, training on 1 million papers here is like, nothing. That's, it's over in the 0 bin region. And
no, but it did start with, I suppose, BERT or something, which has seen.
Well, BERT has seen a lot of text.
Yeah.
Oh, but let me now say another thing here. So it only uses the first, I think, 128 subword units of the title and abstract. That probably doesn't get you much past the first sentence. I'm going to say that from the title and the first sentence of an abstract, you can't tell what the paper's about.
Okay. Okay, all right.
I think that the green line is just a non-starter.
Okay.
Yeah.
Okay, anyway, that was just a comment. And then.
All right,
unless
so
other
you
people
want to
have
try a
questions.
demo. So here's, let's see if I can get to the, how do I get out of here?
That should do it, yeah.
I want to get to a website.
Okay.
And then say, so what is, this keyboard is,
It's a French keyboard.
it's a French keyboard, I need a French typist.
Oh, steady,
What was that?
steady.
Oh,
No,
no.
it's all right, just.
Pay no attention.
Uh-oh. Shabna, you okay?
I don't want to sign in. How do I go in without signing in?
Scroll down and say no or something.
Accept all.
Okay, all right.
Oh, it is on the GitHub. Okay,
Okay.
fine. Okay. Did I say GitHub? Yeah.
Yes, you said GitHub.
All right. Now, darn! All right. Yeah, the hardest part of this demo is clicking on the link. There! Success. Okay. So this is the documentation for the website. And here's the query that, that's one that's known to work. So there are a lot of different, there's a little query language, but if you just give it some keywords here, it'll find a paper. And then, would it help if can I make this bigger somehow? How do I do that? How do I hit plus? Did that work? No, it doesn't.
It's fine, Ken. It's
All right.
fine. We can
You
do
guys
it.
have better eyes than I have.
Yes.
Okay. So, at any rate, what you can see is from the Deep Walk paper, here's a bunch of papers. And these papers are pretty highly cited, so that works. Now, I can add to this another keyword. This, pay no attention to the horrible query language. Oh, but I need help in finding an ampersand. Where's the ampersand?
Actually, someone who uses the French keyboard, can they help? Okay.
Please come up here, I can dictate.
Lucas will help you.
Okay, so I want you to type ampersand spectre equals.
Ampersand.
Okay, hold on. It's coming.
I know you can't translate. Yeah, right. Who could have come up with a spectre? I'm sorry, embedding equals spectre.
Embedding equals spectre, okay.
Yes, carried your turn.
Boom.
So
Okay.
this is what Spectre does with the same query. So there you can see that's the dupe to the query paper. That's the same paper as the Deep Walk paper, but it has no citations. So, and the abstract is identical to the original pretty much, and the authors have a big overlap. So that's, I think, why
Yeah, cool.
matching on the text of the abstract is, I think, not such a good idea. Seems like a good idea, but it's not.
So
Okay.
who in the audience wants, yeah.
The thing is that if I give the demo, it's too much cheating. So I obviously cheated there, and I can't type. So we need somebody to dictate, somebody to type, and I'll just look here like embarrassed while you embarrass me. I do want to say that if there are glitches, so you will definitely find things where even the website just breaks. But I think it'll work on many papers.
Anyone wants to try a paper?
Yeah, please. Or you type away.
So I need to type exact match? Or
No,
just
no,
like a
no.
set of
This
keywords?
query, just some, after search equals, type some keywords that come to mind.
How did you guess? Not Z, W.
Oh, but you did, with that, who knows what that one's going to do, right? Yeah, right. You can't type on a French keyboard either.
No.
It's a good answer?
No,
I don't know this
No,
area.
this is just a starting paper.
That's
Eason,
the
this is
starting
Florian's paper.
But remove the spectre equals. I think you're going to do better without that.
Okay, so the first one is Florian's paper. We know that.
I mean, it's not too far off. I mean, you have lexicon free, so it's kind of. Sorry, I will try to defend. I'll be the advocate here, but the lexicon free seems kind of, at least the word makes sense. And
The second one seems to make sense as well. It's
and
posterior
CTC,
based.
as you'll see tomorrow, is kind of FST, right? So we'll take it for a match.
If you pick any of the similar to this, it will use that paper as a query.
Oh, we can use one of those papers as a query. Okay.
So you
just click here.
Yeah, just click one of the similar to there.
So let me like the lexicon here.
What's happening? It's done?
Yeah.
Okay.
All right. It's a little too fast for me. Okay. I don't know if I look at this. I'm out of my area. I don't know if these. So one of the hard problems is to know what the good answers are, and I can only know the good answers in the literature I know.
Okay.
Anybody want to try something like completely different, like medicine or something? Does anybody know anything other than speech and language in the room? How about something involving non-English languages?
Okay.
Is there anyone here who speaks French?
Yeah. No, you don't want to do similar equal to, right? Yeah, there you go. Search equal to. Nope.
How do you put space in
You can
Percent.
type space or %20. You can just type space, yeah. Oh, yeah, I have no idea what it's going to do with the French characters, but it's terrible. Oh, it's not, or it is? Yeah, all right.
All right, I wanted to try.
Okay, what does it look at? What have you tried?
So I typed French keyboard in
I
French.
didn't do the. So the website needs some help with other, keyboard keystrokes. It only handles. You got to find a French word that's in ASCII.
But how about we remove the clavier, the keyboard, and just French? Maybe there will be keyword, something related, French related, right?
Just like keyboard layout or something.
I just have French in French. Huh?
Oh, so the first answer is coming from Semantic Scholar. It's the rest of this is trying to match things that are close to that. All right, enough of that. Sanjeev, you had your favorite topics, right?
Yeah, no, I asked you to look for, there is this paper on, Yenda, what is the lattice tree MMI paper called? Purely sequence trained models. Purely sequence, no, single L. Sequence trained. Oh, trained. It's a Q.
Yeah, the A and the Q are swapped.
Okay. Yeah, that's the one.
Okay, so we can do that with, this is, I think, using proposed.
Yeah.
But we could try it. Oh, I've forgotten where the ampersand was.
Luca, where's the ampersand?
Oh, I see it. I found it.
Can just type on the key ampersand and you don't type any dead key. Yeah. Yeah, there you go. You see, you're getting better.
I found it. All right.
We'll convert you.
Oh, but where's M? Oh, it is. Yeah. Look at that. All right. So that first answer is terrible, isn't it?
Yeah. No, I see what's happening because this phrase lattice-free MMI isn't used in non-relevant papers, so it just doesn't match anything else. So it matches on other things.
Yeah. All right. So, would people? I know that I went really fast through the approximate nearest neighbors. But that's a very technical topic, so I went through it very fast because I didn't think that everyone would want to know, and but I could certainly spend time on it. But maybe you'd rather have an evening to. I mean, we said I think we're supposed to be done around 4:30. Yeah. So, Oh. So Emma's got.
No, it's okay.
Pay no
so
attention.
If anyone else wants any other paper exercised, we can try. Otherwise, we can
You
thank
can always
Ken
try
Steen.
it offline
Yeah.
too, right?
And Ken, what we can do is there might be people interested in the the linear algebra stuff you were telling us earlier about the approximate. By the way, approximate nearest neighbors is a really fun problem to work on.
And
so if you're
very
interested,
general.
stay back and Ken can talk to you some more. But let's call today's proceedings to an end. All right, and tomorrow we start at 9:30. Right? Okay, so we don't do the morning thing tomorrow, and we'll just start at 9:30. We'll have a slightly longer evening tomorrow. I'll wrap up with thanks to sponsors and various people who helped us. All right, okay, see you all tomorrow.
Take care.